Hi everybody and welcome to Numbers Online School. Today we'll be going through bijections as they are used in combinatorics, and then after that we'll be doing some problems whereby we'll be using bijections to solve them. So what's bijection? By definition, whenever you're given two sets A and B, a bijection is a map from A to B such that it is both injective and surjective at the same time. So that means that no two elements of A are mapped to the same element of B, and every element of B is an image of some element of A. So a bijection is defined between two sets. So if you're having a set A and another set B, a bijection is simply a function defined on the set A and whose image is on B in such a way that it pairs up elements from A to unique elements in B. So by injective, it means that the function of A, if for some two elements, A and B, so X and Y of A, in a way that the function of X equals to the function of Y, then X necessarily has to be equal to Y. So this is what we mean by injection. So we say that a function is injective if for some two elements of A function, if their functions are the same in B, then they have to be the same. And by surjective, we mean that for every element Z of B, there exists an element, say for instance T of A, such that the function of T equals to the function of Z. So whenever you have an element of B, then we know that there exists an element of A whose function is equal to that particular element of B. So this is what we mean by surjective. So a function is said to be surjective if it satisfies this condition here. And so a bijective function is a function which satisfies both of these conditions. So it is both injective and surjective. So in this particular case, we can take a look at an example. For example, if I have a set, so this is my set A, it contains the first three alphabetical letters, and another set B, which contains the numbers 1, 2, and 3. So if I define a function from A to B in such a way that I map A into 1, B into 2, and C into 3, then in this case we see that the function that does this mapping is a bijective function because it pairs up the elements of A into the elements of B. So in this case, whenever you have this situation where you have a set A, a set B, and an existence of such a function which is bijective, and this implies that the size of A has to be equal to the size of B. Mostly, of course, because when A and B are finite sets, then this bijection implies that there are as many elements in the set A as there are in set B. So in this case, we have this equality, which is brought about by this bijective function. Okay, so this gives us a way to pair up every element from A with some corresponding element of B. So that is what I was trying to explain here. There is a one-to-one correspondence between between the elements in the set A to the elements in the set B, which gives about this inequality whenever the sets are finite sets. Now, whenever we encounter an elementary combinatorics problem, usually the sets involved are pretty much finite sets. So in this case, whenever you find a bijective function from two sets, you will have that the size of A has to be equal to the size of B. So this is what we'll be concerned about today, and we will use this theory to solve some of the problems that I have listed here. So at this point, you can try to pause the video and try problems on your own. But for now, I'll go through the first problem. So let's see. The first problem says that let n be a positive integer. In how many ways can one write a sum of at least two positive integers where the order matters that add up to n? So what does this problem mean? So for instance, let's take n equals to 3, for example. When n equals to 3, in how many ways can we write 3 as a sum of at least two positive integers where the order matters? So for example, I can write 3 and express it as a sum of 2 plus 1. At the same time, I can express it as a sum of 1 plus 2. So this is where what we mean by the order matters. So 1 plus 2 is considered to be different from 2 plus 1. So we count these expressions as being two different ways to express 3 as a sum of positive integers. And at the same time, there is 1 plus 1 plus 1. So we can also express 3 as a sum of 3 ones, and this is clearly different from the two previous ones. So at this point, we can convince ourselves that these three ways are the only possible ways where you can express 3 as a sum of at least two positive integers where the order matters. So in this case, when n equals to 3, the number of ways is 1, 2, and 3. So in this case, when n equals to 3, the answer is 3. So let's try another example. Let's try 4, for example. When n equals to 4, how many ways can we express 4 as a sum of at least two positive integers where the order matters? So just for starters, we can start with, we can express 4 as sum of 3 plus 1. That we can also express this as sum of 1 plus 3. Okay? How many other ways can we do this? You can express 4 as a sum of 2 plus 2. That's another way, which is clearly different from the previous two ones. And another way, you can express 4 as a sum of 2 plus 1 plus 1. Okay? Which is different from from previous ones. And again, just from this partition, we can try to rearrange the ones we have here. We can express this as 1 plus 2 plus 1, and also this can be expressed as 1 plus 1 plus 2. So all these are just different ways of expressing 4 as a sum of at least two positive integers. So I think we have at least one more, right? You can express 4 as a sum as sum of all ones. Okay, yeah, so you can express 4 as 3 plus 1 as 1 plus 3 as 2 plus 2 as 2 plus 1 plus 1 as 1 plus 2 plus 1 as 1 plus 1 plus 2, and then 1 plus 1 plus 1 plus 1. So how many ways are there? There's 1, 2, 3, 4, 5, 6, 7. So in this case, we have 7 possible number of ways. Yeah. So I think that's all of them. Yeah. So there are 7 possible number of ways of expressing 4 as a sum of at least 2 positive integers, where you can order the parts of the summands into different orders. So in this case, when n equals to 4, the answer is 7. But again, we have to show this. We have to calculate this for all the possible positive integers n. So we have to come up with a general formula for the answer whenever n is a positive integer. So how can we do this? There are several ways to do this. I mean, you can try to spot a pattern for small cases when n equals to 3, 4, 5, and so on, and then you can try to prove by induction. But for the purposes of this lecture, we'll try to use bijection as an approach to solve this problem. So we can try to redefine this problem in another way, where instead of looking at a positive integer as a single unit, you can think of it as, for example, when n equals to 3, you can think of it as three dots. Okay, 3 dots on a line. Okay, now how can we redefine this function in terms of this representation of 3? So I can define a partition of 3, for instance 2 plus 1. We can simply express this as a splitting. So we split 3 as a sum of 2 and 1. So we split there, and we express 3 as the sum of 1. So this represents 1 plus 2. Okay, so this representation can also be expressed in this form, where we split this representation of 3 at this point right there. In this case, we get 2 points on the left and 1 point on the right. So this is a representation of this partition here, 2 plus 1. So how about this representation of 3? In that case, you might have guessed it, we're going to split at these 2 points, two parts, to get a representation of 3 as a sum of 1 plus 1 plus 1. So in other words, we have found a different way, a much more visual way of expressing this partition of 3 into parts which are clearly at least 1, because in this case we are either putting a splitting part here at the middle, or at this part here, or at both. So in this case, we can start to recognize here a pattern and try to find a general way of solving this problem. So let's try again for n equals to 4. For n equals to 4, we have again 4 points. 4 points. And again, we want to express 4 as the sum of, in that way, sum of at least 2 positive integers where the order has to matter. So in this case, again, a representation of 1 plus 3 can be represented as a split right there of these 4 points, where on the left hand side we have only 1 point, and on the right hand side we have 3 points. So here we have 1 plus 3 to represent this partition here. There is also this representation that we saw earlier. So in this case, again we have 4 points here, and then we have a splitting at the middle there. So we have 2 points on the right and 2 points on the left. So again, if you have a representation as 1 plus 1 plus 2, again similarly, we have two splittings at here and at here. So it's 1 plus 1 plus 2. So I guess at this point, you can see the pattern here. This number of ways of partitioning 3 or splitting 3 into parts which are at least 1 is happens to be the exact same way of putting partitions between these points in the middle. So in this case, you can have one partition or two partitions, or you can have all three of them to represent 1 plus 1 plus 1 plus 1. So in this case, you can redefine the problem as counting the number of ways in which you can split 4 points using a certain number of at least one splitting parts. So in this case, when n equals to 4, we have several options. In this case, we can put a splitting part here, or at this point, or at this point, or at that point. Okay, so we can put a splitting point, sorry, at this point, or at this point. In this case, it is the same as saying that we have to fill these middle spaces, okay, by either a yes whenever you put a split, or if you don't put a split, then you put a no. Whenever you put a split, then you put a yes. So for the representation that I have represented here as 1 plus 3, this representation can be mapped to the 3-letter word yes, and then no, and then no, to represent this partition here. So in this case, we have settled a partition on the first part to represent a yes, and since there is no partition here, we can simply put a no, and for no partition here, we can simply put a no. In the case of this representation, that means we have 1 point, 1 point, and then 2 points. This representation can be represented by these bars, where in the first place we have a bar, so we put a yes. In the second place we have a bar, so we put a yes, but in the third place we don't have a bar, so we simply put a no. Okay, so in that case, this letter can represent this partition here. So we have a map from this partition into this letter. And as we saw earlier, this partition is mapped to this 3-letter word. And of course, at this point, you can try to figure out on your own. But for example, this partition of 2 points on the left, 2 points on the right, this partition can be represented as the 3-letter word of no, then yes, then no, to represent again the 4 points, and then you split here at the middle. So here you don't have a bar, so you put a no. At the middle we have a bar, so you put a yes, and at the end we don't have a bar, so we put a no. So in this case, this partition here of 2 plus 2 can be mapped to this 3-letter word. So at this point, it is clear that we can define a function. So maybe we define A as the set of the partitions n, let's put it as an, partition of n into integer parts where the order matters. So yeah, it's the same number of ways that the problem is asking us to evaluate. Is the same as the number of ways you can write n as a sum of positive integer parts where the order matters. So it's exactly the number of ways in which the problem asks us to find. And then you can define another set, call it to be n, to be equal to the number of n minus 1 letter words whose letters are either yes, either y or n. So in this case, we define another set to be n, depending on n, of course, which is the set of all the possible three-letter words whose letters are n or y, to represent the yes and the no's for the bars that we have saw earlier. So in this case, as in the case when n equals to 4, we can find a function from an into bn, like we described in this example, in such a way that this function from an, so a function from an into bn in such a way that it is both injective and surjective. So in this case, just in the previous example, even if you give me a random three-letter word whose letters are either yes or no, for example, n and then y. In this case, I can find a partition of 4 which directly maps into this into these three-letter words. In this case, I will have 4 equals to 3 plus 1. This partition of 4 will directly map into this three-letter word, and it is easy to see why, because whenever you have 4 points, and then this representation can be expressed in this form, where you split in the left hand side has 3 points, the right hand side has 1 point, and in this case, as the way we define these three-letter words, we don't have a bar here, we don't have a bar here, but we have one here. So this can be represented by a no, and a yes. So in this case, this function is both bijective and surjective because the function is actually well defined. And so in this case, can we actually say that because we have found a bijection from an to bn, can we say that the size of an has to be equal to the size of bn based on the theory that we have just discussed previously? So in this case, there is a little bit of correction. Actually, we are almost there, but there is one partition that we need to look at, the partition of 4. So we can express 4 as 4 by itself, like that. So that is a partition by itself, but this can be represented by, when we write the 4 dots, we decide not to put a bar at any of the 3 partition points. So in this case, this partition of 4 is represented by n. So we don't put a partition at all on either of the spaces available. So in this case, the partition of 4 by itself is represented by this 3-letter word. But in the problem, we're actually not interested in this partition because we say that it has to be the sum of at least 2 positive integers. So in this case, we have to modify our set Bn into the set of 3-letter words of n minus 1 letter words whose letters are either n or y, except the letter with all n's. So except that one with n minus 1 n's. So all the other n minus 1 letter words with y's or n's, we exclude the one which has all n's to exclude this trivial partition of n by expressing n as n by itself. So in this case, we actually do have a bijective function from a n to bn as we have just defined here. And by the theory we have just saw, we can easily actually bn is easier to calculate in this case, because in this case, as you can see, because we have 3 spaces and we have to put either yes or no, and it's easy to see that the number of ways has to be 2 times 2 times 2, which is 8, because at each of the points you have to put a yes or a no, and at each of the points actually whenever you put an n here, does not depend on whether the first place was an n or a y, and does not depend on the last part. So actually this what we decide to put on the on a place at this word does not affect the other places. So in this case, you have 8, 2 times 2 times 2, but again the n has to exclude this element. So in this case, you have to subtract 1 so that you can get the 7 number of 3-letter words, which actually agrees with what we saw earlier. And we saw that for n equals to 4, the answer will be 7. And similarly, for n equals to 3, by similar computations, we'll have 2 times 2 minus 1, which is 3, which is what we agreed on the very first part. So in this case, this turns out to be actually true for the general case. Whenever you have this set an and this set bn, we define the bijective function, and in this case bn is easier to calculate compared to an, which makes us to conclude that an has to be equal to bn, and bn has to be equal to, because we have n minus 1 places to fill this n minus 1 letter word, except for this one which has all n's. So in this case, you have 2 power n minus 1, and then we subtract the trivial word which contains all n's. So in this case, this will be our final answer for the first problem. So for general n, the answer will be 2 to the n minus 1, and then that power of 2 is subtract 1, which actually agrees to what we have saw for the smaller cases. For the smaller cases, when n equals to 3, then we get 3. When n equals to 4, then we get 7. So that's it. We're going to continue with problem number 2. And problem number 2 says that each of the vertices of a regular nonagon has been colored either red or blue. And we're required to prove that there exist 2 congruent monochromatic triangles, that is, triangles whose vertices are the same color. So in order to describe this problem, we'll start with constructing a regular nonagon. So in this case, a regular nonagon is a regular polygon with 9 sides. So here's an example of it. Here it has 1, 2, 3, 4, 5, 6, 7, 8, 9 sides of equal length. So this is a regular nonagon, and we have been told that it has been colored in either the vertices, this corner points, they have been colored in one of two colors, either red or blue. So maybe in this example, we'll try to color it. So maybe here you can put a red color. You can put a red color, maybe red there, and maybe another red here, and maybe another red here. Okay, so we have 4 red points, and then for the other vertices we color them in blue color. So we have a blue color there, a blue color there, a blue color there, a blue color there, and finally a blue color over there. So we have a total of 9 points, 4 of which are red and the rest 5 are blue color. So this is an example of a configuration in which we are describing in problem 2, and we are supposed to prove that there exist two congruent monochromatic triangles. So what does a monochromatic triangle mean in this configuration? By a monochromatic triangle, we mean that it is a triangle whose all of its vertices are of the same color. So for example, you can have a triangle like this one here, okay, in which all of its colors are equal to red. So we have a red color there, we have a red color there, and we have a red color there. So this is an example of a monochromatic triangle. So for example, you can have another triangle, this triangle over there. This triangle is not monochromatic because although these vertices are blue, the other one is a red vertex. So in this case, this triangle is not a monochromatic triangle. So in this example, we have a monochromatic triangle, and we are required to find another monochromatic triangle which will be congruent to that. So if you can find a monochromatic triangle in this configuration, then the statement is true for this example. So maybe I can try to find another set of points. For example, in this case, you can have this triangle. Okay, you can have that blue triangle, blue monochromatic triangle. Now this triangle, as you can see, we have this length which lies between these two segments, and in this red triangle we have this length which lies between these two segments, and we have in this blue triangle we have this segment which lies between 1, 2, and 3 segments of the nonagon, and similarly we have this red segment lying between 1, 2, and 3 segments of the nonagon, and lastly we have this longest segment of the blue monochromatic triangle, which lies between 1, 2, 3, and 4 segments of the nonagon. And of course, we also have a similar segment on the red triangle with 1, 2, 3, 4 sides of the monochromatic triangle. Now, because this triangle, because this polygon is a regular polygon, then this side will have to be of the same length. So this length is equal to this length is the same as this length, and this length is the same as this length. So in this case, these two triangles, one is of which is red and the other one is blue, they are actually congruent to each other. So we have managed to find an example in which that statement is true. So in this example, the statement is true that we have managed to find two monochromatic triangles which are congruent to each other. Now we have to actually show this for all the possible configurations of coloring these vertices. So there are lots of ways to color the vertices. This is one of them, where we have colored four of these points as being red and the other to be blue. So we can try another example and try to prove actually to find these two monochromatic triangles for also those other configuration. For instance, we can try to color all of the vertices to be maybe, for example, blue, and then these two triangles again will be blue triangles, and they will still be congruent to each other. So that example also works, but we have to actually show that it is true for all the possible colorings of the vertices of the given nonagon. So in this case, in order to simplify our work, instead of going through all the possible examples, we can try something which is more smart. We can try to characterize the triangles which are congruent to each other, or in short ways, you can try to describe a triangle which is inscribed in this nonagon. So for example, we can try to define the length of this segment of the red triangle running from this point to the other point as being equal to the number of segments of the nonagon which is on the other side of it. So for example, we have this triangle. So on the other side of this triangle, bounded by this segment, we have 1, 2, and 3 number of segments of the regular polygon. So in this case, we can define the length of this segment as to be equal to 3. And similarly, we can define the length of this segment to be equal to 1, 2, 3, and 4. So you can define it to be of length 4. And for the same reasons, you can define this segment, its length to be equal to 1, 2, because it is bounded by 2 segments of the nonagon. And for another example, you can try maybe this triangle. You can describe the length of that triangle as being equal to 1, and the length of this one to be equal to 2, and the length of this segment to be equal to 1, 2, 3, 4, 5, 6. Okay, so in this triangle we have we can define it as 1, 2, 6. So in this case, we can define every triangle whose vertices are in this nonagon as a triplet of three numbers. So in this case, this triangle can be described by 3, 4, 2. Okay, and the other triangle, this one here, can be described by 1, 2, 6. And this triangle here, similarly, you can define it by, for example, this one has length of 1, 2, so you can define it by 2, and then this segment can be defined by 1, 2, 3, 4, and the last segment can be described by 1, 2, 3. So can be described by this triplet of points, so 2, 4, 3. But remember, we want to describe congruent triangles as being exactly equal to one another. And so we want this blue triangle to actually be in some sort of ways described in the same way as this red triangle. Now this red triangle was described by this triplet of points, and this blue triangle was described by this triplet of points. So we want in some sort of ways this to be exactly the same as this. So in other words, we want to describe the triangles as triplet of points where the order of these numbers is irrelevant. So in this case, we don't care the order in which these numbers are written, as long as what is in this triplet is exactly what is in this triplet. The triangles will always be congruent to each other because the corresponding lengths will actually be of the same size, and that will force those triangles to be of the same color. So in this case, we can find a map. Sorry, you can define a set A to be the set of triangles of triangles whose vertices whose vertices are vertices of the regular nonagon. And then we describe another set B to be the set of these kind of triplets. Now, before we define B, we can actually um, see another property of these triplets. You can see that the sum of the number of triplets, of the number in the triplets, for example, in this case we have 3 and 4 and 2. If you add them up, you get 3 plus 4, which is 7 plus 2, we get a total of 9. And similarly, for this case, we have 6 plus 2 plus 1, which is 9. And this will be actually true for all the possible triangles here, because remember, we're adding these segments corresponding to the other sides of a segment of a triangle. So in this case, because there is always a total of 9 segments, each of the segments of the nonagon will be included in the calculation of the length of exactly one of the sides of any triangle in this inscribed in this nonagon. So in this case, the total number of numbers in these triplets will always be equal to 9 for the 9 number of segments bounded by the nonagon. So in this case, we can describe B as the number of triplets A, B, C, whereas A, B, and C are positive integers. So they are positive integers in such a way that their sum A plus B plus C is equal to 9. So in this case, we find a function from A to B, sorry, a set from A to B, whereas we have described here, for any triangle, you can describe a triplet of A to B, where B is a set of triplets A, B, C, where the entries are positive integers with sum equal to 9. So this clearly describes what we have just tried to explain before. And in this case, you can see that the function is actually not it is not injective. It is not injective because whenever some two triangles like this triangle here is of course not equal to this triangle, but they are congruent. But in this case, they are mapped to the same triplet. So in this case, the order is irrelevant. So this red triangle and this blue triangle, they'll be mapped to the same triplet. So in this case, we need to sharpen the definition of A to describe it as a set of congruent triangles whose vertices are vertices of the regular nonagon. So in this case, this function will actually be an injective function. And for other reasons, you can clearly see that it's also a surjective function. Whenever you have a triplet of points, for example, 1, 1, 7, this is a triplet of points which belongs to this set, and the sum, because the sum is 9, and you can easily find a triangle, for example, maybe this triangle, which is mapped to this triplet, based on our definition of this function from the triangles to the triplets. So this function is actually injective and it is also surjective at the same time. Now, after we have described a function, it is now easier to calculate b as compared to calculating a. So at this point, you can calculate the size of b. The size of b is simply the number of partitions of 9 as a sum of 3 positive integers where the order does not matter. So in this case, because 9 is not a large number, we can actually list all of the possible triplets. So in this case, we can express 9 as a sum of 7 plus 1 plus 1. So they have to be 3 numbers, and they also have to be positive integers. So you can have 7 plus 1 plus 1. You can have 6 plus 2 plus 1. We can have 5 plus 3 plus 1. We can have 5 plus 2 plus 2, right? We can have 4 plus 4 plus 1. We can have 4 plus 3 plus 2. And then we can have 3 plus 3 plus 3. So actually I've tried to express 9 in terms of the partitions in an increasing order, so that it could be easier to go through all of them. So in this case, we have 1, 2, 3, 4, 5, 6, 7 possible partitions of 9 as a sum of 3 positive integers where the order is irrelevant. So in this case, the size of B has to be equal to 7. That is the size of B. Okay. be equal to, because we have at least 5 blue points, and each triangle takes exactly 3 of these blue points. Each of the triangle that we are trying to form from this set of 5 points will be equal to 10, 5 combination 3. So we have 10 possible triangles out of those 5 which should always be available. And in this case, because by this result here, we know that there are only 7 possible number of incongruent triangles that you can make out of the vertices of this nonagon. So at least, because 10 is greater than 7, there are some 2 triangles which should be congruent with each other. Because you can never find more than 7 incongruent triangles whose vertices are formed by the vertices of the nonagon. That's what we have tried to prove initially. So in this case, because you can always find some 10 of them, then in this case, because 10 is greater than 7, some people might say by the pigeonhole principle, some 2 of these monochromatic triangles will be congruent to each other, and that will be our solution for the second problem. So at this point, the major work was trying to establish this condition that we cannot find 8 different incongruent triangles which are described in this format, inscribed in this nonagon. And from that, we can actually find some 2 triangles of the same color, which are also congruent to each other. And of course, when we have at least 5 of the points being red, you can just do the same procedure, and then you can find some 2 red triangles which are congruent to each other. So in this case, we are done. Now, as for the third problem, we are going to determine the number of walks from 0,0 to 5,4 steps up to the right triangles. Okay, maybe there is something else. You always have to go either 1 step to the right or 1 step up each time. So at each point, you have to start from this point, and then you have to end at this point. But at each step, you take 1 unit distance to the right or upwards. So for example, you can start from this point, then you can go all the way to here, then you can go 1 step up, then to the right, then 2 steps up, then 2 steps to the right, then 1 step up. So this is one of the possible paths from this point to this point. Every time you have to take either 1 step to the right or 1 step upwards. So in this case, you can take this other path. This is also a valid path. So as a non-example, you cannot go like this, because here you cannot go downwards. At each of the points, you either have to go to the right or upwards. So in this case, maybe you can go upwards, and then you have to go straight forward. So you cannot go downwards or to the left. You always have to go right to the right or upwards. So in this case, we want to find the possible number of paths which are described in that pattern. And in this case, we'll try to find another set which is easier to count compared to the number of paths from 0,0 to 5,4. So in this case, I'll find another set A. So we describe the set A as the number of the paths from 0,0 to 5,4. Okay, so this A, number of paths from 0,0 to 5,4, which observes this rule of going either one step to the right or one step upwards. And then we define another set B, which is the set of 3 letter words of nine letter words whose letters are U or R. So just as an example, we have seen this part. So this part can be described as 2 steps to the right. So we started with 2 steps to the right. So you can describe that path as right, and then upwards, described as a U, and then right again, 1 step to the right, and then 2 steps upward. You can describe that by 2 U's, then 2 steps to the right, 2 steps to the right, and then 1 step upwards. So like that. So you have right, and up, right, up, right, up. Okay. So that's one of the examples. Let's try another example. This path, it went upwards, then right. So it started with up, and then right, and then up, and then right again. Up, and then right. And then 2 steps upwards, 2 steps upwards, and then 3 steps to the right. 3 steps to the right, so 3 arrows. So we can describe this path as this, how many levels? So it has 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. So it always have a length of 9 words. And you always have either R's or U, depending on the turn that which this path takes. Either it goes to the right or it goes upwards. So at this point you can try a number of other paths, and what you will notice is that whenever you describe this word using the those paths, you always find that if you count the number of reds, then you always have 5 reds, 5 reds, and you always have 4 number of B's. So 5 rights and 4 number of U's. So in this case we have 1, 2, 3, 4 U's, and we have 1, 2, 3, 4, 5 number of reds. Similar to this case, you have 5 number of reds and 4 number of U's. So for example, the path that goes all the way to the right and then all the way to the upwards, it has 5 number of R's beginning and then ending with a consecutive 4 number of U's. So in this case, you can define this function B as 9 letter words whose letters are either U, maybe you can modify this. You can say that it consisting of 5 R's and 4 U's. So this set of 9 letter words consisting of 5 R's and 4 U's. It does not matter the order in which the R's are placed or the U's are placed. As long as there are 5 R's and 4 U's, you can it has to be in this set. So for example, maybe I can write R, U, then R. This word clearly clearly is in this set by definition, because we have 4 U's and then we have 1, 2, 3, 4, 5 arrows, and this will be an image of the path that goes 2 steps to the right, like this, 2 steps to the right, then 4 steps upwards. So you get 1, 2, 3, 4 steps upwards, then 3 steps to the right. So 1, 2, 3 steps to the right. So this is an image of a valid path as described by the problem conditions. So in this case, we clearly see that by the way we have defined these letters, we have managed to find a function, a bijective function, in fact, from the set A to the set B. Now the set B is easier to count, as we have done in other previous examples. You can count the number of the size of B. So the size of B, because we have a total of 9 words and some 4 which are all U and some 5 which are all R's, and then some of you may recognize that this has to be equal to 9 factorial, and then because we have some of them which are repeated words, 4 of them which are blue, and 5 of them which are R's, this will be actually our final answer. 9 factorial over 4 factorial times 5 factorial. Number of ways you can form a 9-letter word using 4 R's and 5 U's. So in this case, our final answer will be equal to 9, choose 5. And calculate this to be 9 times 8 times 7 times 6 times 5 over 5 factorial, and how much would that be? So it will be 63 times 2, a total of 126 number of possible paths, number of possible words in B. Now because of that theory, we know that the size of B, because of this bijective function, has to be equal to the size of A. So in this case, the number of paths has to be equal to 126. And that will be our final answer for that problem. Thank you for watching. You're welcome again to Numbers Online School. Thank you.